of the computers. Okay. All right. Suppose that of the computers on campus, only CS2 and Mat1 are currently under attack by the intruders. Then we can go ahead to be able to ascertain the true values, meaning that true values is finding out whether it is true or is false, or is valid or invalid. So we want to find the true value of ACS1, ACS2, A Mat1. So when you talk of ACS1, who can tell me the true value of ACS1?
Sir.
Yes.
Please, it's false since only CS2 and Mat1 are under attack.
Yes, so ACS1 is false.
Yes, sir.
That's true. What about ACS2?
It's true.
Exactly. A Mat1.
It's
True.
Good. Because you have been told that CS2 and Mat1 are those that are under attack by intruders. Okay. So that is not something we should worry ahead on. Now let's come to the third example. Now let's K of xy denote the statement x equals to y plus 3. What are the true values of the proposition K of 1, 2, K of 3, 0? So let's start with K of 1, 2. What's the true value of K of 1, 2?
Sir, false.
False. Because
Yes,
if you insert, you realize that when x is 1, y is 2. That's going to give us 1 equals to 2 plus 3.
5, which is false.
Which is not true, which is false. Now, when it comes to K of 3, 0, x is 3, y is 0.
It's true.
That's
true.
you don't need to try to know that it's true.
It's true.
Good.
Calm down.
So at least I have some people on board now. Good. So you realize that this particular session is not difficult, right? Good. Good. So now you are good to go. All right. So we still go ahead with some other examples. Here we want to be able to find out in this statement, if x is truly greater than 0, then x is defined as x plus 1. In other words, we are going to have x plus 1 assigned to x, given that x is truly greater than 0. That's the meaning of the statement here. Now here, we say that P of x is truly greater than 0, right? That's a propositional function. X is truly greater than 0. Now, upon taking a value for x, the true value of x is obtained. Now, and the decision of whether to execute this is made. So we can only execute this statement, x plus 1 assigned to x, provided the x value is known and it's greater than 0. That's the meaning. So if my x is -1, there is no way I'll come here to add a 1 to the x.
Okay.
If my x is 0, in fact, there's no way I'll still come here because 0 is not greater than itself.
Yes.
0 is equal to itself.
Yes.
The only way I can come here is when x is, let's say, 1. When x is 1, when x is 2, I can also go there. When x is 3, I can also go there. That's the meaning. Okay, so x is truly greater than 0 means that we are looking at positive integers. Okay, and that's something I have to let you know. X is truly less than 0 means that we are looking at negative integers or negative values. Okay, now let's look at precondition and postconditions. So normally when we talk of preconditions, basically there are some values which are
Please,
valid.
a quick one.
All right, go ahead.
Yeah, please. So does it mean the predicate in the computer program? So the first example we did. So does it mean in this case we have an implication in this case?
Yes, yeah.
So the implication with this very implication, our premise is that s is greater than 0 there, and the conclusion will not be. So if this is false, the conclusion will not hold. So we don't have a predicate there.
Perfect. So I'm glad you brought this thing up. Remember when we were looking at the implication?
Yes, sir.
We said that the implication is if P then Q.
Thank you. Yes.
So assuming that x is really greater than 0 is a p.
Yeah.
And then the K becomes x is defined as x plus 1.
Yes, sir.
Then this whole statement can be written as P implies Q.
Implies Q. Yes.
Okay.
Where if P
Where the P here is x is really greater than 0.
yes.
And then we have the Q to be x is defined as x plus 1. In other words, x is equal to x plus 1.
Oh.
So as Nelson was trying to explain, we know for implication that, of course, the first value here is the premise or the hypothesis, and then the second value here is the conclusion. Okay. So once both premise and conclusion are all true, you're going to have the output to be true. If they are all false, you're going to have the output to also be what? To be true. But the only way we can be able to establish it to be false is when this particular premise or the hypothesis is true and the conclusion is false. That gives us an output of a false. But basically, all we are trying to say is very simple. The only way we can be able to know that everything is true here is we need to make sure that this particular hypothesis, in this case, is satisfied. Once it is satisfied, we can be able to come and execute it. What does it mean? So let's start with the first part. This is true, that is true. We're going to have an output to be true, right? So if x is really greater than 0, in other words, x is 1, x is 2, x is 3, we can come here and execute here. So this is true, that is true. We're going to have an output to be true. Let's look at the case whereby this is false, that is false. We're still going to have an output of what? Of true. Why? If the x here is a negative value, right? It means that we are not going to execute here. So that will be false. And of course, we're also not going to come here. That will also be false. So at the end, the whole output will still be true. Because if I don't do left, I don't do right, then that is true.
Yes.
It's like you not being able to establish two things at a time.
Okay.
Then it's true. So if I, assuming I'm supposed to be voted into power to become a president, and I make a statement that if you vote me into power, I'm going to reduce taxes,
Yes.
right?
Yes, sir.
Imagine you don't vote me into power, and at this situation, taxes is not voted. It's not
Join
reduced.
the meeting.
Then I don't have any issue here. It is too true. It is only when I became a president that was what I was going to say that taxes is going to reduce. But this is the case I didn't become a president, and taxes are still not reduced. What is the first statement there? I've not done anything wrong.
Yeah.
Another example I can also give you for that same implication is if you are supposed to get an A, right?
Yes, sir.
Assuming you get an A,
Yeah.
or you get 100% in my exams, and probably you pass in my assignment, then you pass the course.
Yes, sir.
If you don't get 100%, right?
Yes.
You don't pass my assignment or the I you're going to write, both are false. Of course, you fail.
Yes.
That is nothing. That's true. It is you who actually didn't execute all the two parts.
Yes.
Now let's come here. If this place is true, right?
Yes,
In other words, x is really greater than 0. Let's say we have a value like 1. We have a value like 2. And then when I come here, I'm expected to come here, but I didn't come here. This is false. Then the output should be false.
Yes.
Which makes sense because no matter what it entails, once the left-hand side is met, right, I should be able to execute this part and I should be able to have my true statement. So I am basically, that's how the whole situation would be like when it comes to the implication. But at this situation, if you really check this very well, it is actually looking at a by implication stuff, meaning that if this is established to be true, you're going to get an output of true. False, you're going to get an output of a false. Okay. But we are not really linking it to other by implication or implication. All that I want you to be able to understand for sure here is once the x is given and the x is really greater than 0, we can execute this part. That's it. If the x value given is not really greater than 0, we cannot execute this. That's all. Okay. Now let's look at the preconditions and the post-conditions. So for preconditions, we're actually looking at valid inputs. For post-condition, we are looking at valid outputs. So if you are given a valid input, of course, you can have a valid output. Now, let's look at this particular statement. Consider the program X is assigned to temp, a variable called temp. And then we can also have X is assigned to, sorry, Y is assigned to X, and then temp is assigned to Y. So the question that arises here is that the predicate for the precondition is P of XY. We have this input A assigned to X as the initial values, and then B assigned to Y as the second initial value. So we can say that this A and the B are the valid inputs, which we call the preconditions. So once we have those preconditional values, we should be able to establish our output. So how do we get the output? We know for sure that this X is A, this Y is B as the initial values. So if you go ahead to find the post-condition means that we're going to have the output. And our output we are looking for is X, which is assigned with a Y, and then Y, which is assigned with a temp. That's it. So if I come here, I know for sure that from this beginning, this temp will be assigned with an A. So temp is now A. So let me write it. So temp is A. So I'm going to put A here, which is going to be assigned to temp. So the variable temp will contain A. Then when I come here, I'm going to have a Y, and a Y from the precondition is a B. So this B here will also be assigned to X. So now the output of X will be B. Can you see that?
Yes.
Now when I come to temp, I know that this Y, we already have to assign to the temp.
Yes.
So in here, this guy is going to be an A.
A. Yes.
He is going to move to Y.
Yes.
So at the end, the output of the post-conditional values is going to be X assigned with a B, Y assigned with a A. That's what you can see here. So that's it. Provided we have access to the preconditional values, in other words, the valid inputs, we should be able to have a valid output, which we call the post-condition. And that's what you can understand here, okay?
Yes.
Now, let's look at quantifiers. So quantifiers is leading us to understand quantification. In that quantification, we should be able to come across things like there exists. This symbol, I'm sure you've come across it somewhere before, which we call there exists. And this symbol for all. So these are two symbols we need to be able to have a fair idea of what they mean. So in terms of quantifiers, they are words which are used to express the extent to which a predicate is true over a range of elements. Remember, we are saying that for predicate logic, we are moving beyond understanding a particular statement to look at a wide range of statements to make an understanding of it. So we can have things like for all, and for all is this symbol that you can see. And then some, we can also have some as one of these. Then we can also have a few, then we can have many, then we can have none. But at this situation, this means that there exists. When we talk of there exists, it means that we are looking for at least one. Right? There exists a particular student here who understands what I'm teaching. If I'm able to find that particular student, then I'm using this symbol. If all the students in this class understand what I'm teaching, then I'm using the for all symbol. Hence, quantification is a way of creating a proposition from a propositional function, a predicate using quantifiers. I want to be able to check the extent of which people understand what is happening. If I'm able to make the statement that everyone in this class understands what I'm teaching, and then I'm good to go. Can I have that statement established? If I can, then I can use this universal quantifier. If I cannot, then I can go ahead. There is this one particular student or there are some students in the class who understand what I'm teaching, then I can use this quantifier, then I'm good to go. So this is for the universal quantification for all. This symbol. And this guy is like A10 upside down. And this one is for the resist. Okay. So there are the area of logic that deals with predicates and quantifiers, we know it's for predicate calculus or predicate logic. So we don't need to worry much about it. Now let's come to domain.
Quick question about the other slide. Yes,
Okay.
yeah. So here, in this case, for the existence, just as you are saying, that one, even if at least one of them exists, it holds, right?
Yes.
Then the first one, the universal one, that one, it has to be all inclusive, like everything within the set of variables you are considering,
yes.
values you are considering.
Perfect. So for the universal,
So what if
everyone inclusive? We can't leave one out.
Okay.
So like this particular class, I'm having 101 participants, excluding myself, we have 100.
Yes.
So for me to be able to deal with universal, it means I'm looking at everyone on board. I'm not skipping one.
Yes.
If I'm dealing with existential, I want to find at least one. If I find one person, I'm okay.
Yeah.
If I find two people, it's still the same.
Okay.
Are you with me? But
Yes,
for universal, everyone inclusive is what I'm thinking about here.
Makes sense.
All right. So we can move on now, right?
Yes.
So with that understanding, then we can now come to the domain. The domain basically becomes like a set, or let's say all possible values under consideration in the universal set. So that's what I just made reference. So assuming in this class, let's assume there are 100 students. The domain becomes all the 100 students under consideration. Now, assuming I'm only dealing with integers, the domain becomes all set of integers under consideration from negative infinity to negative 3, negative 1, negative 2, negative 1, 0, 1, 2, 3, all the way to positive infinity. If I'm dealing with only positive integers, then I'm only actually dealing with 1, 2, 3, 4, 5, 6, 7, all the way to positive infinity. If I'm looking at positive infinity, strictly less than 10, then I'm looking at 1, 2, 3, 4, 5, 6, 7, 8, 9. That becomes my domain. So the domain becomes the set of all possible values or elements or members under consideration. Okay. So the set of possible values that a variable can assume becomes the domain. The variable can be the x, the y, the z we are looking for. Remember, we looked at P of x. So that x here, the domain becomes all members that the x can pick or can take. Now, so the universal quantification of P of x is the statement P of x for all values of x in the domain, all inclusive, right? You're not leaving one out. Now, again, this is denoted by using the notation as I mentioned for all x P of x, where this particular notation, right, is a universal quantifier, which means for all or for every, right? For every possible value, for all possible values. An element in the domain for which P of x is false is called a counterexample. Remember, we are looking at universal quantification. We want to be able to be sure that every member in the domain, right, is captured.
Yes, sir.
In other words, we want to find out that if everyone is punctual, then we are looking at the fact that Kofi Ama Ajwa, Kofi Ama, whatever, Kweku, Menu, everyone. If you come across Ajwa, who is not punctual, then Ajwa becomes a counterexample. Now, the funny part of universal quantification is that once we find a counterexample, then the whole of for all x P of x becomes false.
Yes.
So you go back to the illustration we were making from beginning, whereby when I'm chewing peanuts and one of them, or granules, and one of them is sport, it affects everyone. Okay. Yes. And to the extent I want to throw the granule in my mouth away. So once I'm assessing every member in the domain, and I find one of them that makes P of x false, then the whole of P of x becomes false because I've come across a counterexample. So for universal quantification, because we cannot access every member in the possible set, we are looking for what we call a counterexample. If you find a counterexample, P of S becomes false, because the counterexample that makes the whole P of S become false. You okay?
So the probability that majority will be true is much.
Yes. But we don't care about majority being true. We only care about the counterexample making it false.
So with the existence and therefore, so if just like you are saying that if we found one counter example, meaning the for all will be false. Now,
Yes,
with
for-
regards to the existence, if we have all within the domain, it's still true, right? So we just need at least one for it to be true. But now we have all within it.
Okay, so I get you with the existential, but let's hold on and let's understand the universal first.
Okay.
Because now we're on the universal.
Right.
For universal, we want to be
So I
able
have
to
a
access
question.
every member in the universal set. If in assessing, the first element is true, the second guy is true, the next one is true, the next one makes the propositional function true, I am good to go. If I get to maybe the 10th element, and when I find P of 10, and I realize that P of 10 makes it false, then that 10 becomes a counterexample. Hence, the whole of the P of X becomes false. Meaning that in universal quantification, because you want to be able to ascertain that the whole for all X, P of X is true, your main focus is to look for that particular counterexample, for that particular bad nut, which is going to make P of X false. Once you find that, you draw a conclusion that the whole P of X is false. I'll give you a typical example. Assuming I'm saying that before the class ends, for me to be able to say that everyone is punctual, I don't want to hear any noise in the class, no matter what. Imagine mistakenly someone asks a question and afterward he forgets to probably mute, and there's a noise. I draw a conclusion that the whole class, no one is punctual. That's how the counterexample works. If I find one, I don't care about majority, I don't care about the 99%, which is still true. That one particular person makes the whole thing false. Okay, so here the domain must always be specified whenever for X is used. The meaning of for X, P of X changes when the domain changes. Don't forget, once the domain changes, the for all X, P of X will change. Assuming I was dealing with integers and I realized that it was false, probably when I go to a different number set, it might not be the case. If maybe I was dealing with the whole set of integers, now I come to positive integers. Maybe positive integers might be true, but maybe all integers, the counterexample is with a set of negative integers. That's it. Okay, so still with the universal quantification, let's look at some example before we come to existential. Now, this first example is that let's P of S be the statement X plus 1 is really greater than X. What is the true value of the quantification for X, P of X, where the domain consists of all real numbers? For real numbers, we need to know that we are looking at concatenation of rational numbers and irrational numbers. And we need to understand the fact that rational numbers are numbers which are always of the form A over B, for example, where A is an integer, B is also an integer, and then the B will never be equal to 0.
Yeah.
It cannot be equal to 0 because any number over 0 is undefined. That is for rational numbers. Then I come to irrational numbers. Irrational numbers, you can deal with repeating decimals, right? Like I have the square root of numbers and other stuffs, the sets and so forth. Those becomes irrational numbers. So what we are saying is that once I can concatenate rational and irrational numbers together, I get what you call real numbers.
Yes.
So now the question now says that the domain is set of all real numbers. Now, if I pick any real number at all, that is X, and I add it to 1, or I add 1 to a real number, will I get a number greater than X? That's the thing here.
Yes. Yes.
So I can pick X to be 0. If I add 1 to 0, of course, the number 1 will be greater than what?
0.
0. Be good. If I go ahead and I pick a number like maybe 1.5, and I add 1 to 1.5, I'm going to get to a 2.5, and 2.5 is bigger than 1.5. So no matter the possible combination of positive real numbers, at this situation, I'm going to have this to be true. Let's come to negative real numbers and check and assess it and see. Let's assume that this x here probably is -1, for example. I'm going to have -1 plus 1, which is going to give me 0. Is 0 greater than -1? Anyone?
Yes.
Yes. 0 is greater than -1. That's true. So let's go ahead. I want to have maybe -1 point or -2.5. -2.5, I add 1 to it. I'm going to get what? -1.5.
Yes.
Is -1.5 greater than -2.5?
Yes, sir.
Yes.
So at this situation, no
Yes.
matter how I do the possible combination, the answer will be true.
Yes, sir.
You okay on that?
Yes, sir.
I cannot find a counter example. So
Sir,
since I
sir,
cannot find
please,
an example, then
sir,
I'm
please
going to
go
have-
over again.
So what
Sir,
I'm
please
saying,
go over again.
all that I'm saying is very simple. I want to be able to find out a particular counter example. Now, the counter example I'm looking for is if I'm able to go through the whole statement or the possible set of real numbers, because here the domain is what? Set of real numbers.
Yes.
And I just explained set of real numbers as numbers which are combination of rational and irrational numbers. So I assume you're all with me on the same page, what
Yes,
a
sir.
rational number is. So we move on that. Now, what it means is this. I'm just going to use try and error. When I say try and error, this is what I'm going to do, because you cannot be able to go through all the real numbers in this world. Because if you ask me, I cannot list them. I can only list some of them and bring 3 dots to denote to infinity.
Yes.
So I start with simple numbers I can think of. I can start with 0. If this x here is 0, right? 0 plus 1 is greater than 0, which is true.
Yes.
Now, because once I have 0 plus 1, I'm going to get 1 at the left-hand side.
Yes.
And I'm also going to have this part to be also 0. So I'm going to have 1, which is really greater than 0, which is true. There's no two ways about that. So 1 is really greater than 0.
Yes.
Now let's go to positive real numbers. I can pick a number like 0.1, for example, for x. So I'm going to have 0.1 plus 1, which is going to give me 1.1.
1.1.
1.1 is really greater than 0.1.
Yes.
No matter how I go ahead, if I can pick 10.8 or whatever number you can think of, all right, I'm going to have 10.8 plus 1, which is going to be 11.8. 11.8 is really greater than this 10.8.
Yes.
At this situation, what do I have? I'm actually going to have it also to be positive,
Yes.
or to be true. We come to negative numbers. That's where the confusion is. So I pick a number like maybe negative 0.5, for example. Now, negative 0.5 or negative half, if I add it to 1, I'm going to have what? Positive
0.5.
Now, this positive 0.5, of course, is greater than negative 0.5.
Yes.
We good on that? Now, let's go ahead and pick a bigger number. Let's pick a number like maybe negative 1.5. Now, when I pick negative 1.5 for x, and I add 1 to it, I'm going to have what?
Negative 0.5.
0.5.
Yes.
Now, can we see negative 0.5 is greater than negative 1.5?
Yes.
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 That's true, because if you're looking at the negative numbers, the one getting closer to 0 is bigger than the one which is far away from 0. So once I can establish that, then there's no two ways about that the whole of this particular P of X statement will always be true, irrespective of the value of what? X in the domain of real numbers. And that's why the whole thing is true, because I didn't find any counterexample. Now, let's come to the second example and see whether we can find a counterexample. Maybe that one will bring the understanding. Let Q of X be the statement X is really less than 2. What is the true value of the quantification for all X, Q of X, where the domain consists of all real numbers. We are still with the real numbers. We understand what a real number is. Concatenation of rational and irrational number. We good. Our main focus is to look for a counterexample. So this statement says that irrespective of the value of x, right? The value of x we are going to have will always be less than 2 to make it true. Meaning that if I can get a value that will be greater than 2, then this statement will be false.
Yes.
And you and I know for sure that we can get a value like that. Assuming x is 2, assuming x is 3. Is 3 less than 2? No.
It's false.
So that becomes false. So even if x is 2, right? 2 is not less than itself. So that is false.
Yeah.
It's
false,
the whole
yeah.
of this thing. It's false. So I'm good. I have a counterexample. So once I have a counterexample, I don't care about the rest. That's it. So here, x equals to 3 can be a counterexample. X equals to 2 can be a counterexample. X equals to 2.1 can be a counterexample. X equals to 3.9, 3.8, whatever value you can think of can be a counterexample.
So I think the most important thing right now is if you don't know your domain, you can never get this right.
Perfect. If you don't know what real numbers are, you can never get this right. Now you're with me, right?
Yes.
I'm sorry, can you please go over this example again? I got distracted.
Which one?
This second one, this very one.
The second example.
Yes, please.
Okay, so the second example, if x is, let's say, 3, right? The question is 3 less than 2? No.
So,
Are you with me? That's false. So once you get
Yeah.
then you draw a conclusion that the whole of this statement is false. You don't care about the rest.
okay.
So your main task is to look for a counterexample. In other words, to look for something that will make Q of x false. And the only way Q of x can be false is when we have Q of 3, Q of 4, Q of 3.2, Q of 2 itself. That's it. Once I get that, I don't care about the rest that make it true.
So for the answer, you wrote false and you wrote s is equal to 3. But s is equal to 2 also is also 1.
So there's an example. We can have x equal to 2. We can have x equal to 2.1. We can have x equal to 10. We can have x equal to whatever number you can take. Counterexample is finding one number.
Just 1.
Just one. So you can bring s is equal to 3.9. You can bring 2.1, whatever. Okay. So the counterexample is not listing all the members, just finding one of them. At least anyone at all. To justify.
Okay.
If I understand, are you trying to say that the counterexample is purposely false or to prove that the statement is wrong?
Yes, to prove that the statement is false. That's it.
Okay.
And once I prove that, it's like you having the bad nut you're achieving. If you cannot find a counterexample, then of course you can say that it is true. But the fact that you cannot find a counterexample and I can find a counterexample doesn't mean that you are right. So you need to be sure that you can find the right counterexample. Now let's look at the second example, the last example, and see something. Suppose that P of x is greater than 0. What is the true value of the quantification for all x P of s for the domain of integers? Remember, now we have moved away from real numbers, we are integers.
Yes.
Can it be true or can it be false? I don't know.
Hello, sir.
Yes.
It will be
example.
false
Why?
because when we use from any number, any decimal, 0 is greater than any decimal. So when you put negative 1 there, negative 1 is not greater than 0.
Okay.
So that will be the counter example.
That'll be a counter example. Okay.
Yes,
All the
please.
negative integers will be the counterexample.
Will be the counter example.
Okay. So remember, as I mentioned, you don't need to list the set of counterexamples. Your main task is to list at least one.
Only one. Only one.
Like the way we had here.
Okay.
Are we okay on that? All right.
Okay.
So this particular statement
It's
is
false.
going to have false. At this situation, even 0 itself is a counterexample.
Okay.
So please, I have a question.
It's true.
Yes, please go ahead with your question.
So please, so if the truth value is false, should you have to write the counter example, or you could just leave it as false?
If the true value is false, no, you need to justify why it's false
Thank you, sir.
with a counter example. Okay. All right, so we can move on to existential. Okay, still with the inverser, there are still some examples. Let's see quickly. What is the true value of 4x p of x, right? Where p of x is the statement. Oh, time is far gone. X is really less than 10, and the domain consists of all positive integers, not exceeding 4. So here, the domain, we are looking at positive integers, which is not exceeding 4. So looking at positive integers not exceeding 4, meaning that we are looking at values like what?
Less than or equal to. It's less than 4.
Less than 4. 1, 2, and
0
3.
to
1, 2, and 3.
Remember, 0 is not a positive integer. Don't forget that.
Yes, sir.
0 is a neutral number.
Yes.
Okay. Now, to confuse you the more, if I say non-negative integers, then what I mean by that is I don't want to list negative integers. I'm looking at only 0, 1, 2, 3, infinity. So non-negative integers will include positive integers plus 0. Don't forget that. Now, if I talk about non-positive integers, what it means is that I don't want to think of positive integers. It means
Yeah.
I need to look at negative integers plus 0.
Yes.
Mhm.
Once I really say positive integers, I'm not looking at 0.
Yes.
I'm looking at 1, 2, 3 to infinity. So in this case, positive integers not exceeding 4, I'm looking at 1, 2, 3. That's it. And I'm done. So I want to be able to check and see whether when I put 1, 2, 3 inside, I should be able to get it to be true. Which of course, you don't need, oh, sorry.
to be true.
Sir,
You don't need
not exceeding 4. Is 4 is inclusive, right?
not exceeding 4.
4 is part.
Yeah.
4 is part.
So-
4 is
Yes.
included.
4 is included.
Or
right?
is it
Yes, please.
Yes.
So meaning
So
that 4,
the
sorry.
statement is true.
So the statement is true. So it's an assignment. I'm actually not solving it for you guys. But
Yeah,
I'll
so
just-
many. I'm going to one up.
That's what I put. But the main thing you have to look at is you need to look at the last one. Be careful with that one. What is the true value of 4x? X is really great. S is greater than or equal to X. The domain consists of all real numbers, right? So go and think about that. I think someone is actually writing on my screen. The person should stop that. Okay, so now let's come to existential. So for existential, because someone is writing on the screen, I have to stop sharing and share again. Just a second. Okay, good. Now, existential quantification means that we are only looking for one of them to make the whole statement what, at least one of them to make it true. Now, there is just an element x in the domain such that p of x will be true. That's it. That's the meaning of existential. Unlike universal, we are looking for one of them to make the whole thing false. In existential, we are looking for one of them to make it true. So if you come to the comparison here, you realize that, but before the comparison, let me read this thing to you. This is denoted by using the notation, there exists xp of x, where there exists is the existential quantifier, which means there exists or there is. Similar to for x, a domain must be specified when there exists is used, and the meaning of there exists x p of x changes when the domain also changes. That we don't have issue with. So let's look at a comparison between inverser and existential. So for inverser quantifier, when it is true when p of x is examined for every x in the domain. That is when we can say that for all x, p of x is true. Now, for existential, it is true when we have been able to get one of the x's in the domain that makes p of x true. That's when the existential is true. Now, when we come to when both of them is false, let's check when for x p of x is false. For it to be false, in this case here, right? We can only say that this for x p of x is false when we have a counterexample. That's it. So there is an x for which p of x is false, and that x becomes a counterexample. That we don't have an issue with based on the example we saw previously. Now, what about when we can say that existential is false? We can only say existential is false provided we have scanned through all the possible values in the domain for X. And we didn't find any of them that made it true. In other words, all the possible values in that particular domain, when we check P of X, it is always false. We check P of X, it is always false. We never came across a P of X that was true. And that's why we are saying that it is false when P of X is false for every element in the domain. So that's a comparison. Now, with this comparison understood, we can now go ahead and also have some. Benjamin, please don't write on my screen. Okay. So with this understanding, we can go ahead to also establish this example. Let P of X denote the statement X is truly greater than 3. What is the true value of the quantification for X, P of X, where the domain consists of all real numbers? So here, for us to be able to understand this, we are looking at all real numbers, meaning that everything inclusive. So our main task is to look for a particular real number that will make X greater than 3. Now, of course, if I pick 4, 4 is greater than 3, right? And 4 is a real number.
Yes.
So I'm good to go. I can say that this is true.
Yes.
Because I can get one number that can make it true. Now, let's come to this example. Let Q of X denote the statement X equals to X plus 1. What is the true value of the quantification there exists X, Q of X, where the domain consists of all real numbers? What does it mean? What it means is simple. If I pick any real number at all in this world and I add 1 to it, I should get the same real number. Let's start with a 0, always a neutral number. If I add 1 to 0, I get 1. I don't get 0.
Yes.
It doesn't mean that I'm done. I should still go ahead. Let me look for any number because existential means I'm looking for a number in the domain. So I can go ahead and pick 100. If I add 1 to 100, I get 101. I don't get 100. Let's go to negative numbers. If I pick maybe negative 10 and I add 1 to it, I'm going to get negative 9. Negative 9 is not the same as negative 10. So no matter how I do my permutation and combination, I will never and ever in this world get a real number that when I add 1 to it, I'll get it. So that's false. We good? So that's up to you to do your possible combinations.
Oh, guys, let's
Okay.
stop writing on the screen, please.
All right. So now look at when the domain is empty. For the domain to be empty,
Hello, sir.
yes.
So with the negative 10 plus 1, does that mean the first X always represents the answer when doing
Yes,
the comparison?
in this case, we are saying that the X is the negative 10 or the negative 100 or the negative whatever value you are picking. But the 1 is fixed.
Yes.
Because the 1 is part of
So
the
when
predicate.
negative 10 plus 1 is equal to negative 9, does that mean the representation of the first X is the negative 9 when doing the comparison to know whether it is false or true?
No.
Okay.
I get where you're coming from. This X is negative 10. If I add 1 to negative 10, this means I should get negative 10.
Okay.
So I getting negative 9, it's not the X, it's different. The precondition I chose was negative 10 for X, meaning that once I add 1 to it, I should get a post condition of still negative 10, but I'm getting a negative 9, which is not true. Okay, so because someone has written on my screen, I'm going to go ahead, stop sharing and share again.
Guys, let us.
All right. Good. So when the domain is empty, what happens? If the domain is empty, then we can say that for XP of S is always true. That's strange, right? Again, we can also say that there is this XP of x is always false. That's confusing, right?
Why?
Yeah, very confusing.
Yes, good. That's why you are doing predicate logic. So it is very simple. Because of time, I don't want anyone to explain. So let me go ahead and explain it. Because I want to learn this. Now, if the domain is empty, right? Meaning that we cannot find any value at all or any member in the domain. We are saying that for all XP of x is always true. It is always true because our main task for universal quantification is to look for a counterexample. Unfortunately for us, the domain is empty. So how can we find a counterexample? We can't. Since we cannot find a counterexample, then we draw a conclusion that for all XP of x is true.
Okay.
Because you can't find any.
We can't find any value that will make it false.
All right.
Again, there is this XP of x is always false. The domain is empty. I cannot find an x, at least one x that will make it true. So because of that, I draw a conclusion that there is this XP of x will always be false.
Yes.
Because there is no way at all I can find that x in that domain that can make it true. Okay, so that's something you can probably reflect on, right? Now, let's look at restricted domains. For restricted domains, all we are saying is very simple. I want to restrict the domain, meaning that if I'm looking at all set of look at this example. Let the domain be the set of all real numbers. Okay. For x less than 0, this x less than 0 means that I've been able to restrict the domain of real numbers to only look at negative values, because when x is less than 0, I'm dealing with negative values, real numbers, right? So for x less than 0, and then I know that my domain is a set of real numbers. This means that I'm looking at negative real numbers. And my predicate becomes x squared is greater than what? 0. So what does it mean? This means that for all real numbers, x with x really less than 0, in other words, with negative real numbers, excluding 0, x squared will always be greater than what? 0. In other words, x squared will always be positive. So when I pick any negative real number and I square it, I'm going to get a positive real number. That's the meaning. So that's it, which means that the square of a negative real number is positive. And where is the restriction coming from? The restriction is coming from here. X is really less than 0. Now let's look at this example. There exists x which is positive. In other words, there is a z which is greater than 0, meaning that the z here is positive. Now, z squared equals to 2. Now, this means that although I'm looking for real numbers, I have restricted the domain to only positive real numbers. So my main focus here is I'm looking for a particular z in the set of real numbers. In other words, in the set of positive real numbers, that's when I square, I'll get a 2. And we know that real numbers is dealing with rational and irrational numbers. And in rational numbers, we can deal with sets, SURDS, which is dealing with root of a number. So I can have root 3, I can have root 4, I can have root 2. So once I have a root 2, if I square root 2, I should get a 2, which is true. There is just a positive square root of 2. That when I square, if I square root of 2, I should get a positive 2, which is good. So the restriction of a universal quantification is the same as universal quantification of a conditional statement, right? So all that we are trying to say here is, once I can be able to restrict the universal quantification, it will always be the same as this implication that we can have. So for x less than 0, in other words, for all negative values, x squared will always be greater than 0. In other words, x squared will always be positive. So if x is negative, then the square of x will be positive. And that's what we have here. If x is less than 0, in other words, x is negative, then s squared will be positive. So that's dealing with conditional statement or implication. Okay, so we're good to go. So in this case, we can say that if z is positive, then z squared will be equal to 2. So we can also say that it's the same as when z is positive and z squared equals to 2. Both cases are all true, hence the output to be true. Remember, with regard to conjunction, the left should be true, the right side should be true to have an output of a true. Okay, so precedence scope variable. This particular one, we are saying for sure that there are instances whereby a particular variable can be bounded to that particular propositional function. Okay, so in this example, we can say that let's
sorry to
assume.
interrupt.
Mhm.
Sorry to interrupt, sir. Someone's hand is up. Emmanuel Mensah.
Okay.
Emanuela Mensah.
Emanuela, please go ahead.
Please, I'm fine now.
Yeah, fine now. Okay, good. All right. So let's go ahead with the precedent scope of variables. So I was saying that the occurrence of a variable is said to be bound when the quantifier uses it. So if there's a particular variable, let's say here, good. In this example, there exists x going into the predicate x plus y equals to 1. This particular x is said to be bound to the existential quantifier because the x is coming from the domain of all the domain under discuss. But the y is a free variable. Y is not expected to be bounded because we don't care whether the s is coming, the y is coming from the domain or not.
Okay.
So this is a typical example of talking about what we are saying here. X is bounded to the existential quantifier because the x is within the domain, but the y is free. It can be part of the domain, it cannot be part of it. That's the meaning. Then we can now go ahead to also look at the scope, right? The part of logical expression to which the quantifier is applied is called the scope of that quantifier. Okay, so let's see. We have in there exists x, p of x, and q of x, or for x, r of x, all variables are bound, right? The scope of the first quantifier is there exists x, is the expression p of x and q of x. So in this case, when we talk of the existential quantifier, the scope is dealing with p of x and q of x. Now, when I come to the universal quantifier, then the scope will be r of x. That's the meaning. So in terms of dealing with the scope, we are looking at where that particular quantifier is attached to, and that becomes the scope and the consideration. So logical equivalence, right? The notation S is equal to this is used to indicate that two statements, S and T, involving predicates and quantifiers are logically equivalent. So we assess what is on the left, we assess what is on the right. If they're all the same, then we can say that it is all logically equivalent. So we want to show that for x going into P of x and Q of x is logically equivalent to for x, P of x, and for x, Q of x. Now, it may be noted that if we distribute this universal quantifier, right, for x to P of x, I'm going to get this. Then I can bring my end, then I can also distribute this for x on the Q of x, and I can also get this, right? Now, we need to be able to understand why it is so. So because of time, I'm not going to prove that to you, but I expect you to go and read on that. Maybe next week when I meet you, I'll be able to showcase you what happens here. But for now, see that this for us is distributed on P of x and then distributed on Q of x. We still come across the De Morgan's law again. So maybe I will use the De Morgan's law to prove something. Then I'll expect you to go ahead to take this as your take-home assignment and prove that for x going to P of x and Q of x is logically equivalent to for x P of x and for x Q of x. So let's come to the universal, the De Morgan. Now, for De Morgan, we came across it, I think, in session 1, whereby we can say the negation of a particular statement, right, or conjunction. If I have negation of P and Q together, it can give me negation of P or negation of Q. Again, if I have negation of P or Q, it's equivalent to negation of P and negation of Q independent. Okay. So when I come here to, I can also be able to say that the negation of a quantifier expression, this and that, is represented as follows. So if I have the whole of this, the negation will be negation of this. If I have the whole of this existential, negation will be this. Now, here too, these are proven. We can say that negation of 4x p of x is logically equivalent to negation of x. Sorry, there exists x, negation of p of x. Again, we can say that negation of there exists x q of x is logically equivalent to 4x negation of q of x. So how do you prove it? Let's prove it with this example. Let's assume I have this example. Every student in your class, okay, we can say that has taken a course in calculus before. Now, so we can write it in this way. For all x, p of x, meaning that every student in your class has taken a course in calculus. That makes sense. Meaning that this particular class, let's assume that everyone here has taken a course in calculus before. So for all x, p of x. Now, then the negation from what we heard here will be re-negating the whole of this. So if you negate the whole of this statement, then we can say that it is not a case that every student in this class has taken a course in calculus before. That is the meaning. If you're negating the whole of this statement, remember, if you bring it is not a case, then you can repeat the whole of the statement. That means I've negated the whole statement.
Yes.
That's why from session 1, I was explaining to you guys that let's be careful how we are negating statement. There are instances whereby you can negate it to change the meaning. And that's a typical case. So we need to be able to understand that if I want to negate the whole of all x p of x, then it is very key to introduce it is not a case. All right. So once I do that, I have the negation of 4x p of x. Remember, my main task is to be able to prove that negation of 4x p of x is logically equivalent to there exists x negation of p of x.
Yes.
Now, if that is a case, then what do we have? So please, this time, I just expect everyone not to ask a question now. Let me finish. Because once you ask a question, you are going to confuse someone. But when I finish, you can ask your question. So now I've been able to have, it is not the case that every student in your class has taken a course in calculus, which is this part. So that is it here. But the original statement was every student in the class has taken a course in calculus. Now, if that is the case, and I'm saying that it is not the case that every student in this class has taken a course in calculus, meaning that when I scan through all the students in the class, I will not be able to find a single soul or a single student who has taken a course in calculus. What it means is this: there is a student in your class who has not taken a course in calculus. I repeat that. It is not the case that every student in this class has taken a course in calculus. Meaning that when I go through all the students, there's a likelihood that it's not everyone, meaning that there can be some students who have taken a course, some who have not taken. That's the meaning. So once I have that negation established, it is not the case that every student in your class has taken a course in calculus. It means that when I scan through, I'm sorry, I might get to one particular student who might take a course in calculus. That's why we're saying that there is a student in your class who has not taken a course in calculus. Or there can be a student who has taken or who has not taken. But for us to establish there exists x, negation of p of x, our main task is to say that there's a student in your class, because this has to be negation, who has not taken a course in calculus, which is true, because it is distributed. We saying that it is not the case that every student in the class in your class has taken a course in calculus. When I go through, some might take, some might not take. But my main focus is to be able to get this. There exists x, meaning that there is a student in your class who has not taken a course in calculus. Now, when I come back here, I should be able to work out the same thing for this example. How? There is a student in this class who has taken a course in calculus. I want to negate that. If I negate that, that is going to be, it is not a case that there is a student in this class who has taken a course in calculus. That's the meaning of this. So once I have this established, then I can come here. If I'm saying that it is not the case that there is a student in this class who has taken a course in calculus, what does it mean? It is not the case. In other words, it is not true that there is a student in this class who has taken a course in calculus. Who can I say what that means? It is not the case that there is a student in this class who has taken a course in calculus. What does it mean in English? Pick one. If I negate this, yes, Derek.
So it means not even a single person has taken a course in calculus.
Okay, not even a single student has taken a course in calculus. That's what it means here, right? It is not the case that there is a student in this class who has taken a course in calculus. That's the meaning. It means that we cannot find a student who has taken a course. Remember, this is different from, it is not the case that every student in your class has taken a course in calculus. What this one means is that when I scan through, right, there's a likelihood I can get some who have taken, some who has not taken. It is not the case that every student, meaning that some students might have taken, some might also have not taken. But when I come here, there is a student in this class who has taken a course in calculus. If I negate it, I get, it is not the case that there is a student in this class who has taken a course in calculus. I will not get a student who has taken that course. So with that same logic, I can be able to use it to prove this, right?
Yes, sir.
That for all students or for every student in the class, right? We cannot have anyone who has taken a course in calculus. Because taking a course in calculus is negated. And I start with, for every student in this class, no one has taken a course in calculus. And I'm good to go. So with this understanding, we should be able to have a fair idea of how this will also be showcased. Show that for all x, p of x and q of x is logically equivalent to for all x, p of x and for all x, q of x. And this one, I expect you to probably pick p of x and maybe make it all true and make q of x some false, some true, right? And then let's see how we can do it. In this case, if I'm saying that for all x, p of x, right, if all the cases here is true, p of x is always true, and q of x is probably some false, some true, I can be able to establish this. I'll leave it to you to try and answer, okay?
Sir, please copy that. Yeah.
A comment has been made, right?
Yeah, that question.
Okay. Let me finalize this slide, then I'll go to questions and answers, right? Just let me finish it. I think I'm left with just this and that. Express the statement, every student in this class has studied calculus, okay? Using predicates and quantifiers when the domain of discuss is all persons. So every student in this class has studied calculus, meaning that if you're a student in this class, you have studied calculus. That's the meaning. So if that's the case, I can easily write it as this. For all students, if you're a student in the class, then you'd have studied calculus, the implication. So because I'm having the every, I can deal with the for x, then I cannot go ahead and deal with what? The implication. If you're a student in the class, then you'd have studied calculus. Again, sorry, when I come here, express the statement, every student in this class has visited either Canada or Mexico. Let's assume it's true. It means I'm still going to have the for x because I'm dealing with every. Then I cannot go ahead to look at my implications. But this time around, I'm not only looking at implications, I'm looking at the definition. So for all x, if you are a student in this class, in this case, we're still going to have the s of x, implies you're going to have c of x or M of X.
Yes.
And I need to be able to put the C of X and M of X in bracket so that I know that S of X implies the whole of this as a scope. Then I'm good to go. All right. Then I can also come here and say that every mail message larger than 1 megabyte will be compressed. Meaning that if there's a mail, right? If there's a mail, remember that every year is dealing with the universal quantifier. But the main thing is if there's a particular mail which is larger than 1 megabyte, then compression will take effect. So however you want to establish larger than 1 megabyte, it's up to you. So I can have for M, which is the mail, S, M, you can make it greater than 1, or you can leave it M, 1, meaning that this M is greater than 1. Some can also be greater than instead of the comma. Then compression C of M will take effect. Then I'm good to go. All right, so I think that should be the end of the slide. Yes. All right, so now let me take your questions quickly.
So the immediate previous page.
Okay.
Yes, so
here, right?
No, sir. The one, the one ahead of this.
Ahead.
Yes. Yeah,
mean
this
here?
one. Yeah, yes, sir.
Okay.
So the example 2. I want to make. Okay, so let me take it from the example 1. So with the example 1, it's kind of a question, an implication where you have to turn it all around. So the domain of the discourse, the all persons.
Mm-hmm.
So I just want to know what makes this statement an implication, because there's no if statement and all that, or it doesn't necessarily have to be.
Okay, so we want to link up. Please mute. Okay. All right. So now the statement is every student in this class has studied calculus. This is actually dealing with a universal quantifier. But when you check it so well, you realize that we are having this statement as a compound proposition. The reason I'm seeing it as a compound proposition is, check it very well. Students in this class studying calculus. But there's no way you can be able to concatenate them together as one, because you are looking at the student as one subject. You can also have a calculus 2 as another subject. Yes. You can have students in this class studying calculus, which are two atomic statements concatenated together. Yes. But for you to be able to see it in that way, then that is where you need to be able to logically reason through and now see that once you are a student in a class, then it implies you have studied calculus.
Okay.
Yes. So it is your ability to be able to decipher that the whole of the statement, aside of the every, which deals with the quantifier, students in this class have studied calculus. It's not a single atomic statement. Rather, you're looking at two different statements. Enrollment, the student is enrolled in a class as one atomic statement. Yes. The student has studied calculus, another atomic statement.
Okay. So it is only one. So if you're a student that you
yes, until you're a student in a class, then you can now have studied calculus. Yes. You can be a student in a different class or a cohort.
Yeah.
Are you with me? The fact that you are all in students at University of Ghana doesn't mean you're all reading DCIT 105.
Yes, sir.
So that's what it means here.
Okay.
Again, when you go to the last part here, it's not every mail that will be merged. It is only the mail that is greater than 1 meg that will be compressed. Sorry. So if the mail is less than 1 meg, it will not be compressed. So that is it. So it's a 2-in-1 atomic statement concatenated together to formulate what we call a compound statement, which is now dealing with an existential quantifier, dealing with the every. So it's a 2-in-1.
Yes.
But when I come here, the third one is actually dealing with probably 3. See, the student is in the class. Some has visited Canada. Some probably have visited Mexico.
Yes.
So I can have S of X as the student. I can have those who have visited Canada before,
Yes.
and those who have visited Mexico. So we are looking at 3 together here. In other words, it's a compound proposition dealing with 3 different atomic statements. Are we okay on that?
Yes, sir. Thank you.
All right. Any further question?
Hello, sir.
Yes, please go ahead.
Please, mine is suggestion.
Okay.
What you are teaching seems like it's not, I may say that is not difficult like that for us to understand. But at times you speed up the speed. So following you with the speed is a challenge now.
Okay.
So I'll plead if you could slow down for us.
Okay, but today you got it right. Everything
Yeah,
was
you started with co and we were able to follow you, but getting to the latter part, the speed was a little bit up.
even today, right?
Getting to the
latter part.
The latter part of the presentation.
Yeah.
Okay.
So we appreciate the first time was okay for us.
That's why the last time I was saying that I'll do my best for my TA to meet you guys. Do you remember?
Yes, please.
Because if I want to go with the pace of my TA, I don't think I can even be here. But the truth of the matter is today I wanted to actually finish session 5.
Okay.
Done it.
But this is session 4, right?
Yeah.
Yes, I wanted to go to session 5, and then next week I can finish session 6, 7, and 8.
Okay.
Yeah, but I understand. If I rush and I finish all the sessions and you don't understand, then it's cost 90.
Yes.
Okay, so I'll do my best to make sure that I'll get everyone on board. At least you're in first year. First year, you still have to take breast milk small. Yeah, we need to smoke.
Very necessary, sir.
I know, but I'll do my best. I'll do my best to.
Yeah, you are doing your best for us. We appreciate it.
Because it's not easy. The course is expected to be with face-to-face interaction where I can write.
Okay.
But now I realize that if the incident that you guys were facing with the teams, it means that for the previous times, most of them have been having issues seeing my screen.
So I think Zoom will be okay.
And that's what I'm thinking. So Nelson, you discuss with your members if you guys think Zoom is okay.
Zoom is very perfect for us.
All right, sir. I'm even trying to record. I think with the teams when I record it, I don't get a sound. So I'll try if the recordings are also have been successful. I'll try and upload them, then share the link among them as well.
Yeah.
So if you think you didn't really follow well, you can watch the video maybe during the week, then you follow. You're on the same page.
Okay. All right, that's fine. So maybe I might not take much of your time. You have another class?
Yes, sir.
Yes, please.
I think starts 1-on-1 in the next 15 minutes, right?
Yes.
I'll leave you guys, and then God willing, next week we can meet early, 1 o'clock. We start with the teams. If the teams doesn't work as we expect, next week I don't think we're going to have much calculation. It's going to be sets, right? So we just stick to our teams. And then I think if there's something that there's the need for more writings on the screen, then I will let you know that we come to the Zoom. So keep the link.
Yeah.
Okay. Hello, sir.
Yes.
Hello. Simply, this very slide is not on Sakai.
I'll upload it right now for you guys.
Okay. All right, sure.
Yeah.
Please, which PDF reader do you use for the sharing? For the slide?
PDF reader. It's PowerPoint too.
PowerPoint. This one is PowerPoint. Okay.
Yes.
Okay. If we're to be this in PDF and open with Microsoft Edge, that one will be when you are writing, we'll be able to see.
Yeah. The issue
but today you saw it, right?
Yes. I'm talking about Google Teams.
I mean, they're talking about Teams, right?
Yes. When it's in PDF and you open with Microsoft Edge.
Okay.
you're able to write with that.
Okay, but strange enough, some were actually seeing what I was writing on the Teams, on the power.
On it.
Yeah, so it was showing all right.
It will delay before it will come.
Yeah, it was showing all right, but it delays. But then
It delays.
there's even one challenge. The Apple products are not actually compatible with the Microsoft Teams. Even with
it's working.
Because
I'm
I'm
using Apple.
actually using a MacBook.
I'm also using the MacBook, and when I open it, I'm able to write and do other stuff.
Anyway, that's just by the way. So as I said, if you're going to do a calculation things, I will switch to my to the Zoom. Okay.
Okay, sir. Okay.
If not, you stick to the official thing on Sakai. So next week when we start, you still look at the teams, right?
Yes,
I don't think this week there will be much writings. I don't
So
think.
then next week we'll join early. We'll join like maybe 12:30 so that we can figure them out, so that we will not exhaust the time.
Hello, sir.
But I will see what I can join earlier. Let's see. All right.
Sir.
Guys,
Hello,
yeah,
sir.
let me see. Yeah.
Please, can we upload next week's slides on Sakai for us so that maybe we that I had before?
Okay, I will do that.
Okay. Thank you very much.
Maybe discuss among yourself. If you guys want us to meet earlier, I'll be able to know that we take it out from there, right?
All right. Sir.
Okay.
Okay.
Thank you very much.
Let me leave you guys. All right.
All right.
Safe.